Good morning, everyone. So one of the questions I got when I became an Amazonian from friends and former colleagues is what optimization actually Amazon does, which looking back is a strange question because essentially there's optimization everywhere. And what I'm going to do now, we try to give you an impression of some of the optimization problems that Amazon solves. And for good measure, there will be a machine learning algorithm as well. So I'm going to do a thing that Amazon does a lot, trying to work backwards. So the supply chain network is divided into three parts: last mile, middle mile, and first mile, reverse order. So that's the order we will be going. What makes Amazon special? It's different for everyone, but for me, one of the things that's really special is that when I'm ordering, it gives me an estimate of when it's actually going to arrive. And that estimate is often, I mean, it will tell you, please order it in the next 2 hours, and then it's there tomorrow morning at 8 a.m. And what this does, it builds an expectation of customers. So what I find these days that, at least in the UK, when I go to Amazon, try to buy something, and it doesn't give me an option to be there tomorrow, I kind of feel upset that this is not what I expect these days. So this delivery estimate is essentially from what the whole outbound supply chain network is working backwards from. It tries to give you as fast estimate as it can, and then it does its best to actually stick to it. The other thing I will briefly hint is that, I mean, the selection at Amazon is huge. So you go to a store, you have a selection, but often you don't even know what you're looking for. You go I mean, sometimes people, I'm told, go to Amazon.com to learn what's actually there, what's available, what you can actually get. I will talk about that, what it means for optimization in a second. So how does the outbound network process works? A customer places an order, then you get an initial fulfillment plan. This initial fulfillment plan is essentially a delivery estimate I was talking about. So the system comes up with a way to deliver that package, and its estimated arrival time is what you get as the estimate. Then there's a process of actually picking up the item, packaging up, and sending it out. And between these two, there are several hours. In these several hours, several optimization algorithms keep running and trying to reorganize things to make the network more efficient. So there's a large window here where, again, we are constantly re-optimizing. And then you get a final fulfillment plan when essentially the package is there to go to the outbound dock. And after that, no more changes to the plan. Just for a quick impression of how this looks physically. So inventory arrives, you get these pods. These pods essentially first of all, these pictures are for an automated site. There are legacy sites that are a lot more manual, but the typical automated site now looks like you have these pods that store all the inventory. You have drives underneath. The picking person, well, this is stow, but stow and pick is kind of similar. So this is stow, this is pick. The associate stand there, and the inventory comes to the associate. So it's very lovely. These pods are moving up and down in separated fields, and essentially it comes to you, turns to the right place, tells you where to put the item. So there's a light that tells you which box to put it into. Then you pick it, package it, and essentially this is the final step where the packaged up boxes are essentially flying through a machine, flying underneath a machine, where a so-called slam label is being stuck on it, and that's when it's final. That's essentially the outbound fulfillment plan. But while all of these other steps are happening, again, we are re-optimizing the path of the package. You have the docks. One thing I found very interesting is that this is a so-called fluid loading way of getting the boxes into the truck. The conveyor belt essentially goes into the truck, and the associate just piles up the boxes inside the truck. Some more impressions. There are automated robots picking up packages and sorting them. They are really cool. They are not as flexible and not as fast as a human at the moment. Then you have sub-same stations where the idea is that you have essentially everything in the same building that Outbound needs. And they are designed so that you, in the morning, you place the order, and in the afternoon, you have the item. Amazon sites do offer public visits. I can really recommend it. It's kind of an experience. Okay, so for optimization, we need to optimize essentially the placement and the path of all the packages. And just to give you an impression of the scale, the number of items that Amazon sells is in the tens of millions. So this means that you have tens of millions of items to select from. And of course, this is very skewed. So most of the demand is for the first 170,000 different items, different kind of items. And then you have tens of millions other that are there, you can buy it, but the throughput and the demand is a lot lower. And this is known as long tail in the literature. Not an Amazon thing. It's typical that all supply chains look like this. Okay, just for the scale. So we have the first mile, where essentially it describes the process of vendors dropping off inventory and it getting to fulfillment centers where all the inventory is held. You have thousands of vendors. Then the middle mile is essentially where from the fulfillment center, the inventory gets to the delivery station. You can think about the delivery station as your local post office where those small vans essentially pick up the inventory and deliver it to your house. You have tens of millions packages daily. So these are all daily numbers, thousands of trucks, actually even flights now. And from the delivery station, you have tens of thousands of vehicles to route. So many of the problems that Amazon solves are actually relatively simple in structure or only in logic. They are just insanely large. And all this also means that this is how it looked like in the past, only a few nodes, few delivery stations and few FCs. I think these are actually FCs. Today, this is how it looks like. So these are all the fulfillment centers in the US today. You have these tens of millions of items, and you need to decide where to place them and where to fulfill them from. So the first mile needs to decide where to place the inventory, and then Outbound needs to then decide where to fulfill the orders from. There's one more node type. So we have the inventory inbound nodes, the FCs where all the inventory is stored, the delivery station that I mentioned where the vans and flex pick up the items, and then you have sort centers in the middle. Source center, the idea of the source center is that fulfillment centers first send to a common node closer to the actual delivery stations where you can do an extra separation of steps. So a truck, say, arrives fully loaded with lots of packages going to different delivery stations, and then they are sorted to different destinations. So this is essentially what the source center does that I will talk about in a second. Cool. So for last mile, let's look at an application. And this one will be the machine learning one. So this one, I was surprised when I first read this, that GPS locations are actually less accurate than you would think. So this is for one particular address, the recorded GPS locations when the driver drops off the package. It's essentially all over the place. This is a little bit counter to intuition, right? And when you're driving a car, you feel like the system actually knows where you are. But one thing to notice, especially when you're driving, is that sometimes you make a mistake. So like take a wrong turn and the car seems to continue the other way while driving on the GPS. Essentially, what happens there is that the GPS have a lot of context, right? I mean, it knows you are driving, it knows your speed, knows your directions, and makes an assumption that you didn't make a mistake. When you are dropping off packages and the delivery driver walks up and down, left and right, you don't have this context. So it's a lot more noisy data. And then when you are trying to route your deliveries, then when you have addresses next to each other and all of them this noisy, it's difficult to know which are the actual geolocation for delivery. Okay, I wanted to have a machine learning example, but most of the examples I have the optimization. So let's move on to middle mile. And let's look at the stochastic optimization problem. So in this application, you need to figure out how to get drivers for all the tracks that you need to send out. Of course, you don't know in advance what is the actual route they will take, what is the actual load you need to send from A to B. You know what A to B's normally are, but not what is the expected flow. And you have three kinds of drivers. The cheapest one is the driver who is employed by Amazon. But of course, you often have to have that driver. You have to give him work. Then you can have contracts like a few weeks in advance, you contact a driver to work for Amazon. And then you have the spot market, where essentially you can say, I have this load, it needs to go today from A to B. Who is going to take it for me? And then there's like a reverse auction, people bidding on work. Actually, I have talked to Uber drivers in the UK who were doing it like they're working for Amazon on the spot market. And when they can't find a good enough deal, they just do Uber. For the optimization point of view, this means that you are trying to optimize in a system where you have these three different kinds of truck drivers. The earlier you sign them, the cheaper it is. But of course, your chances of making a mistake because your forecast is more noisy. And then as you get closer to the actuals, the new drivers get more and more expensive, but you get better and better forecast. A very nice, super hard stochastic optimization problem, which also includes a recurrent routing problem at the end. Right? So you have this forecast problem, actually assigning the drivers, and then in the end, the routing problem that you need to have enough drivers to route all your trucks. Another application. So when you are, assume you have a customer even who has placed an order, and you have multiple ways of fulfilling that order. You can even assume that it's coming from the same fulfillment center, but it's going to, it can take two or more different pass options. And you can think about these pass options as, say, pass A being the Amazon. So when Amazon delivers to your door, so the MZR driver, and pass B, you can think about it as the post office. So you just give it to post. And the capacities and costs are usually reversed, so that the cheap option usually is with the limited capacity, and you can we usually think about the post office as the more expensive option, but technically, from Amazon point of view, a larger unbounded capacity. So you have a forecast of what is coming, and you need to decide what package to send on this which pass. So quite often, if you essentially start just with a greedy approach of sending everything to the cheaper, you will use up all your good delivery options. And later in the day, you will probably pay the price, not just in terms of it being more expensive, but potentially running out of fast delivery options. And again, the whole Amazon delivery chain is designed to get stuff to you as fast as possible. So what do you do? Well, of course, you write it up as an optimization problem where you have packages. It's like XL. This is probably going to be the only optimization problem I actually show. So you have variables where each shipment has different pass options. Each of them has a cost. You have various capacity constraints like e-sort capacity or just truck capacity. And interestingly, you also have lower bounds. These often represent things like contractual obligations, like we promise the post office to send you this many packages every day. So what you need to do, you need to solve this problem to be able to route the shipments to the optimal path. Now, we talked about having tens of millions of shipments every day, and everything has several path options. So this problem is somewhat large. The sizes that you see here, like number of shipments, these are sampled sizes. And well, as you can see, the express runtime is somewhat large on these relatively simple problems. This is simply just too large. I mean, normally what happens on these kind of problems is that you build a fantastically huge problem, like 80 million, 100 million columns. Presolve solves away most of it. So you get like 1 or 2 million, but the resolve time is like 20 minutes. And well, as I said, you want to keep re-optimizing as you go. So having such a large offline like optimization problem is not practical. So what we do instead, this problem is very nice for Lagrangian decomposition. So what you do, you essentially do the standard Lagrangian relaxation. You have your dual multipliers, move them up in the objective, and then what you can see is that these are the complicating constraints connecting all the shipments together. So if you take these constraints out, which again are over all the shipments and all the paths, then what remains is a now fairly complex objective and then a simple remaining constraint that just tells you, please route all the shipments. So it's become separable in shipments, which means that this problem is trivially solvable, trivially parallelizable and trivially solvable. It's just essentially a greedy for each shipment, which means that this is super fast. So all your time can be spent on actually just keep updating the Lagrange multipliers. So very nice Lagrangian decomposition application. And it entirely collapses the runtime, which I have some, yeah. So this is an early version that has been presented before, so I can present as well. You can take this time and divide by 10 if you do some more cleverness. So it's a fantastic problem for Lagrangian decomposition. One more thing is that, of course, Lagrange decomposition does give you a primary solution, but as things keep changing, primary solution is not always the best. Things change and you might actually not have a primary solution available for your change state. So what you can often do is just do a dual control. So essentially you harvest the optimal dual multipliers from this problem and make offset these costs by those dual multipliers. Essentially calculate the reduced cost for all the shipments, assuming an optimization problem. That helps for two parts. First of all, it makes a fallback when you don't have a primary solution. It's very fast. And also, when you are sampling the problem, you are sampling in the primary space, you still get a dual solution. So you can still do dual control, even if you are not solving the full problem. And if you think about what this means mathematically, this is essentially a projection to your optimal phase. I think that's true. So essentially taking the Lagrange multipliers as offsets, applying it to the path options, and then just selecting greedily, that's equivalent to projecting the problem to the optimal phase. Cool. I still have a few more minutes to talk about the other big topic, network design. What we see here is two alternative network design approaches. The one on the left is where you have lots of direct lanes. Amazon likes direct lanes because they are very fast, right? I mean, you put stuff on the truck and the truck goes where it needs to be at the end. And what you get is this large interconnected graph. When I said fast, of course, what I meant is that the travel time is fast. So the alternative is to have fewer edges, but of course the flow amount doesn't change. So these fewer edges will be thicker. More flow will be going on them. This means that there will be more frequent truck schedules on them. So you will get more frequently going trucks. So the question in the network design, which one works out better? The one where you go everywhere directly, but relatively fewer departures on each edge, or the one where you have 6 lanes and you go all the time. This is how it looks like on the actual US network. So this is the one where you try to go from everywhere to everywhere, somewhat convoluted. I believe this is closer to reality today than the other one. And the other one is where you have consolidated the edges, go to more source centers, and essentially have fewer edges, but more frequent departures. Unfortunately, what this also means that some of the stuff that was going from, say, here to there directly will now take a detour. And that means that there's one extra place where you are touching the package. Amazon is very focused on touching because touching means when you take an item out of the truck and put it into another one. So essentially how many times you handle the package. That's the expensive part. So the truck is relatively cheap. I mean, trucks is big. There's a huge number of package inside, relatively cheap. But when there's an associate handling them, that's where the real cost is. So actually doing this more consolidated network can often be more expensive in terms of touching because the weighted sum of all the arcs is larger. So never mind you have full arcs, more packages are flowing because now packaging are taking detours. And how does it actually look like in an optimization problem? So this is another fairly straightforward looking optimization problem. You have packages going from origins to destinations, which is in itself is an outcome of another optimization problem deciding the placement model. This optimization problem happens both in first mile and in middle mile. First mile, where to get the how to get the inventory to the right storage facilities, fulfillment centers, and on outbound, how to get the packages to you, how to design a network that will get the packages to you. So you have essentially flow requirements, and usually we solve these problems by a fractional approach. So you know how much flow needs to go from A to D, and there are pass options, and each pass option gets assigned a fraction of what is the amount of flow that will travel on that pass. Then you get simple looking constraints. This is as you can think about this constraint as either this is like the truck capacity. So you sum up all the flows going on that edge with a fraction of how much of that flow will go there. And you get a capacity, which is the number of trucks multiplied by, say, the size of the truck, the volume of the truck. But you can also think about this as under the roof sortation capacity. So this is just not just network constraints, but also under the roof constraints like sortation. And in which case this can, say, be the number of associates you need to work on sortation. The problem with this problem, it's MB hard, of course, but these can be solved to very large proportions. The problem is that essentially it's unbounded how large it can get in the case of Amazon. So a surprisingly difficult problem that you need to solve fairly often. And I think I'm running out of time.